Okay, welcome to my midterm seminar. I am excited to talk to you about expert judgment today, and we'll plunge right in. The URL to the slides is here, so you can later check it out. But for now, we'll carry on with the example. So what I'm going to talk about today is the situation like this. So let's say we have some data about the measurement of this beautiful rainbow trout from Canada. And the fisherman has collected the data, the length and girth, which is like how thick the fish is, and the weight of it. And this is a sample from the data set that a particular fisherman has collected in Canada. This is the data, and we know how to work with it. You can plug it into the model, you can do a lot with it. Then we ask a fisherman to actually describe his experience from the past. What does he expect to see in the next caught fish? It's like sort of describe the typical fish that you can find in this river. And he can give us these predictive judgments. And the reason they're predictive is they're describing the next observation. Before the next fish is caught, we can ask him to give us some sort of measurement of that fish with uncertainty. So it comes as a quantile assessments. So for example, for the length, he gave us median and the 5th quantile and the 10th quantile and 95th and 99. We asked him these elicitation questions to elicit or extract those numbers from him. And I don't go into details how to do that. For that, there's a whole science how to do that, right? For the weight, you see, he gave us the minimum number and the medium and quartiles. And the reason he gave minimum is because the distribution is actually truncated. He is obliged to throw away fish below 7 pounds. So therefore, it's impossible to observe fish below 7 pounds in the sack because he has to throw it away. And just to give an idea that judgments can come in slightly different forms, but these are predictive judgments. And then we talk to the biologist, that's the third picture there, and we ask him to describe how do I find out the length of the fish. And he, based on his judgment, based on his understanding of the fish biology, he said, well, it's linearly dependent on the girth of the fish and the square root of the weight. And therefore, he postulated that model and gave us parametric judgment, which is distribution around the parameters. And see, right now we have for alpha, we have, again, quantiles, or rather, the 10th and 19th quantile. And for, let's say, for gamma, which is a coefficient by the square root of weight, he also gave us the minimum median. It needs to be positive, basically, it says, right? The coefficient by the weight needs to be positive. And for beta, yay, we have the whole distribution. Right, so the normal distribution there, and he basically says that I don't know, just big variance, but I don't know what it will be. But I'm trying to say these are also different ways of giving the parametric judgments, right? So you see the difference between parametric judgment and predictive judgment. Parametric judgment is necessarily tied to the model, and it's uncertainty around parameters. And predictive judgments are just uncertain observations, or rather uncertainty describing the next observation. And the difference is that all the statistics and machine learning and AI and everything talks about data. And my thesis is on that side. So I'm dealing with judgments. That's where the big divide is. And today we'll focus on the other type of evidence that or input you can collect from experts. And I do err sometimes to call that also data from experts. It's not actually data, those are judgments, right? And we're going to talk about these kind of things, not the data, but the judgments. Make sense? Okay, and we're going to come back to this example maybe later on. Okay, so first I need to say why is it relevant to environmental science and why this research is needed, a little bit about my PhD, and then introduce some key statistical concepts that may be novel or, I don't know, unfamiliar, so that you are on the same page when we're talking about the applications. At the end, we'll talk about 2 applications that we've done in the papers. So why is this relevant for environmental science? Well, environmental science is about understanding the problems and solving them, as far as I understand. And many of the problems we cause ourselves, humans, by intervening with ecological systems and messing them up. So understanding human impact is key. On the other hand, this excellent book by Gregory says that structured expert judgment is needed when data is sparse, when monitoring is expensive, and the systems are complex. And it seems like that's what we get in environmental science. The data is sparse because it's vast landscapes, right? Vast variety. Monitoring is quite expensive, and the system is very interrelated and complex. So there is a match, it seems, between the structured expert judgment and environmental science. So I developed these tools to help extract the judgments from the experts and then apply them to environmental domain to solve problems, right? So that's the rationale. So why is this research needed? In a sense, why do we need expert judgment if you have big data, right? Abundant data, why bother? We just collect more samples. And yes, but we discussed sometimes the data is expensive and it's difficult to collect, but not only that. I think there is one more fundamental reason to why we need expert judgment, and that is because it's very core to how we learn from observations. The science is about learning about the world, and you need to start with your prior knowledge. That's necessary. You start with prior knowledge, then you can collect some observations or some evidence from the world, and then you revise your knowledge into arriving into new knowledge. This is very rough, of course, approximation, but that's what Bayesian statistics is all about. So you start with prior knowledge, what we know, then you collect some data, and you arrive at the new knowledge that can be used for decisions or, again, for the next iteration of learning, because science never stops. We keep refining our understanding of the world. So that, in that sense, structured expert judgment is important because it comes first. It actually comes as an input to all of this loop that we're going through. And there seem to be some gaps in structured expert judgment in science which I want to highlight here. One, it seems like the adoption of the structured expert judgment approach is a little bit hampered by very high demand or quite high demand on statistical literacy. Experts are required to understand what the models are all about. In that linear model example, eliciting coefficients for girth conditional on weight on square root of weight is very non-trivial task. In a sense, like you need to tell quite a lot to the expert to get to that knowledge, right? And the fisherman with my fish rod may not understand all of these things. It's difficult. Another one is the choice of statistical distributions are somehow limited. Well, in the paper, which I encourage you to read, I published online, there will be URL at the end. I give an example of the elicitation software that is often used, and it has only so many distributions, and you are encouraged to kind of switch through them to find distribution that fits best, and sometimes you don't find anything that fits best. So there's some kind of sacrifice of precision that happens when you're trying to fit this known distributions to the data. So that seems to be a challenge. And sometimes it's convenience over appropriateness. We sacrifice some precision to say, well, this normal distribution is easy to work with. Let's go with that. Seems to be symmetrical enough. And then there seems to be a lot of methods that are invented to objectify or make analysis objective, basing only on the data. But very few methods that work with structured expert judgment to complement the data. There is also other extreme where structured expert judgment is used alone without the data because it's too difficult to integrate. So we just elicit something from the experts and go on with it. We just elicit predictions. Why do we bother about the model? And the downside of that is that you cannot learn from that. Predictive judgments are impossible to update. So there seems to be these gaps that I'm trying to fill with my research. Okay, and of course, another thing is it takes quite a lot to admit that we don't actually have the data that we need. So talking about the research, I'm trying to simplify the tools for expert judgment and apply these insights to the domain. So far, I have done, I don't know how to move this. To get it out of my way.
Can you just see what's in the chat? Because if there is some problem with the information.
Okay. People are discussing something.
Yeah.
They seem to have fun. It's okay. Okay, so regarding my work, we have published a few articles that are already submitted for publication in the process. One of them is tenets of quantile-based inference, and the other one is called hybrid elicitation of indirect Bayesian inference with quantile-parameterized likelihood. These papers are in the journals, and there are two others that I'm working on right now. Quantile-parameterized priors, one of them, and the other one is related to species distribution model. And I highlighted the keywords, and when these will appear, you will understand that they refer to those four papers, right? So now you can just watch these little bookmarks on the site, and they will refer to which paper we're talking about right now. So there are 4 papers, and one of them is called tenets, the other one is codenamed hybrid, and the third one is QPP and SDM. I'll talk about them at the end. Okay, so first I need to introduce some key statistical concepts. So those are from paper 1 and 3. Most of these distributions will be familiar. Normal, exponential, beta. You might not have heard of Kumaraswamy, but it is a complement to data, or rather it's the same, it's a generalization of the beta distribution with somewhat simpler function. But these are parametric distributions which we all know and love and use. Perfect. And then there are weird kind of distributions that are parameterized by quantile probability pairs. So what's special about them? Look at their parameters. All of them, except for the last one, but more or less the same as well, they have Q parameters, Q1, Q2, Q3. The Meyerson, Logit-Meyerson, which is some iteration on the Meyerson distribution, which we propose in paper number 3, Johnson, quantile-parameterized distribution, and Metalog. These Q1, Q2, Q3, they come from these quantiles that we've elicited from the experts. Remember in the beginning, we elicited some quantiles from the experts, some judgments. So these judgments can go directly as parameters into the distribution. That's what makes them unique. The parameters are nothing else other than the judgments. You get the judgments, you plug them into distribution, you got the full distribution. We'll look at some examples. Metalog is somewhat special because it requires both the P vector and the Q vector, which means that you can have any number of quantiles and any number of, not only 3, but any number of quantiles and probabilities, corresponding cumulative probabilities. And that is a much more flexible, rather maybe even generalized approach to quantile parameterized distributions. So that's the main distinction. And I'll talk primarily about quantile parameterization, or not primarily, but heavily on quantile parameterization, because it's such a powerful way of encoding the judgments from the expert. I've written a package, QPD, and there's a URL at the end where you can install it in R and play with it. Quite a lot of these distributions are implemented there. All right. Next distinction that we need is density-defined versus quantile distributions. Now, the quantile is used here as well, but it's not the same quantile. So let's talk about this one. So density-defined distributions are defined by their CDF, cumulative distribution function, and or PDF. So normal, for example, gamma is in that domain. They're mostly invertible in the sense that they also have an opposite to them, quantile function, but not necessarily. And Meyerson, for example, is quantile parameterized density-defined distribution because it has CDF as well. There are other distributions that are defined in terms of quantile function, but they're not invertible. So they don't have a CDF. Those are kind of weird a little bit distributions. And the reason I need them is because this super general, super flexible Metalog distribution is useful, but it doesn't have a CDF. And that's why it's listed here. So just to recap quickly about the quantile function and distribution function. Distribution function, we all know that's a CDF. It's the way to define this probability distribution, right? With exceedance, they're sometimes called exceedance curve. And the derivative of it is called probability density function that we usually denote it with small f. The inverse of the distribution function is called quantile function, or it's commonly known as inverse CDF. We'll talk about that in a second, the next slide. And but there's also a way to make a derivative of it, and you arrive at quantile density function. That's a derivative of quantile function. And the nice property is that these little q and little f are reciprocally related. They are the same measurement. They're just kind of reciprocally connected. And that allows you to make quite a lot of progress in Bayesian inference, which we'll talk about in slide 5. So a little bit more on quantile functions. Why do we bother about quantile functions? They are a little bit under-researched, I think, my opinion, but they're super cool. If I can get you excited about them, that's already one of the achievements for today. First of all, any quantile function can be written like this. It's capital Q with 3 parameters, mu, sigma, and theta. Mu is location, sigma is scale, and theta is any number of shape parameters that you can plug in. So any quantile function can be written in this form: location plus scale times some sort of basic quantile function, right? I mean, believe me, all distributions have this form for the quantile function. And that's super nice because this basic quantile function can be any non-decreasing function. It doesn't have to be anything sophisticated. Look at these examples of basic quantile functions that I have here. If you just plug in u, you get uniform distribution. If you plug in u to the power of lambda, you get power distribution. If you plug in there 1 minus u to the power of minus lambda, you get Pareto distribution. You plug in minus log of 1 minus u, it's exponential, and so on and so forth. This is just kind of permutation of small changes, and that allows you to do quite a lot. And they can be combined and extended using the Gilchrist transformation rules, and there is a reference for it. Yeah, so we will talk about that, and I already mentioned that the nice thing about them is that you can get to PDF equivalent with this density quantile function. The distribution function is what we know, these kind of S curves, and the quantile function is just looking at the same graph sideways. So, and then all of these curves will be non-decreasing, it will be somehow increasing, and even the U-shaped distribution will be constantly increasing. It's just bended in the wrong direction. That's a weird shaped beta distribution. So the reason, I mean, one of the properties that we used in our papers is the fact that the likelihood for the Bayesian inference can be defined in terms of the quantile function. There are these substitutions that you can make instead of the observations y. You can substitute the quantile function of the depth u sub I, and then the likelihood can be completely expressed in terms of these u, intermediate depths u, that represent observations. If the quantile function is not invertible, like in case of Metalog, then you can use the root finding to numerically approximate CDF and get to the intermediate depths u. This quantile-based likelihood can be implemented with any existing MCMC sampler, and of course you need root finder to get to those u values if they're not available. I'm not going into details, but there are links and you can learn more. So why do we bother about all this? So there are some applications. As I said already, quantile-parameterized distributions can be used to directly encode the judgments of the experts, so that's nice. And here's an example from EFSA, Food Consumption Database, regarding food safety. They collect data on consumption. So look at the chart, right? So we have some summaries of consumption of bitter chocolate from the consumers, and here we have actually 5th, 10th, 50th, 95th, 97th, and 99th quantile. These are black dots on my CDF. And as I said, you can use quantile-parameterized distributions, the ones that I already talked about, to draw a smooth line through them. There are some minor differences, how they hit each line, in a little bit difference in the shape, but the main advantage of them is that they guarantee that the points will be honored exactly. So if the expert gave you those judgments in terms of quantile probability pairs, you are guaranteed to hit them. You may not be able to cover all of them. Here we have 5 points, and some distributions are parameterized by 3 points only. But those points that you do use, you will definitely go through them, right? So that's the advantage. And they end up in somewhat different shapes. And you can see Metalog is weirdly shaped because we use different quantile, but they are like roughly in the same ballpark. So the risk manager comes in and he asks, well, we just got the sample from 2016 survey, actual consumption. Can we update this chart? This is what we've learned up to 11. Can we somehow revise it? And by the way, we're really interested about the upper tail, the extreme consumers. Can you give us some estimates about the extreme consumption of bitter chocolate? Because it seems to be causing problems with uncertainty because the sample is very small, right? So what do you do about that? Well, there are nothing off the shelf that you can use right away because these judgments don't have any uncertainty. So we need to come back to the experts and ask about uncertainty in the judgments. So that's our method. In order to update the judgments, we need to take the QP pairs and allow them to vary a little bit. So those points need to become a little bit fuzzy, right? They need to be able to move around. And then we represent probabilities as relative frequencies from a hypothetical sample. So this is how my interview would go with the expert. We would come back to the expert and say, well, consider a sample of bitter chocolate consumers, say 100 people. According to your assessment, there should be only 24 people that consume up to 1 bit of chocolate a day. So this is based on their judgment that the expert had given. For 24th quantile, he gave us 4 grams of chocolate consumption. There are these dotted lines. They're not actually 25, it's actually 24%. And then we will interpret this assessment as you believing that there is about equal chance that the actual number of morning coffee consumers, the people that consume only 1 bit of chocolate, in the sample will be above or below 24. Would you want to reconsider this value? Give us a different value for the median. So you see the probabilities that he gave us, the expert gave us 24% and then 50, I think it's 52. And the other one was about 82 or 83. Those probabilities can be converted to relative frequencies. So now we're not talking about 24.24, we're talking about 24 people out of 100. And we represent these 24 people as that. See, there's an icon chart there on the left, on the right. Morning coffee consumers, the 24 people are highlighted right now. And we're asking the expert, would you like to vary that number of people in the sample? Give us the low estimate for that, morning coffee, little 1 bit of chocolate, and the high estimate for the morning coffee consumers. And that way we get a triplet of, again, quantile judgments around that value of 0.24. So in effect, we're eliciting uncertainty about probability, but we're never calling it that, and the expert can follow with the questioning. So at the end, we get to this table of morning coffee consumer 24 in the middle with some uncertainty around it, 18 to 30. And after dinner, that's 2 bits of chocolate and sweet tooth and all of that. All this table can be encoded into the Dirichlet distribution so that we can generate samples from that assessment. So this is how prior assessment looks like. We used to have one curve. Now that after we've elicited uncertainty, we actually have a spaghetti plot, which is like a bunch of curves, because the actual judgment of the expert is uncertain. So that's what we have going into data. This is before we have seen any samples. And then the question that our manager asked is about these extreme consumers. So we can summarize the 5th and 95th quantile with uncertainty and see how the actual draws are landing. For the low consumer, we have uniform distribution more or less. For high consumer, it's centered around, I don't know, something like maybe 25 or so, with quite a lot of spread up to 170 or so. So it's quite a lot of uncertainty right now. And then we incorporate the data. And the way we incorporate the data, as I said, the prior will be the Dirichlet distribution. Then we can accumulate the probability using the cumulative sum function, and then plug it into this quantile expressed likelihood, which is also described in the paper, hybrid elicitation paper. You can look at that. So I'm not going into details, but this is very neat way of using the machinery in the quantile functions to update judgments expressed in terms of quantile-parameterized distribution. There's quite a lot of examples. So at the end, what do we get? We get updated judgments. This is the data that the risk manager has provided from the 2016 survey. The spaghetti plot has moved towards the data because the data has weighed somewhat on the judgment. But because the sample is small, we actually have quite a lot of uncertainty left, and the judgments or these bunch of curves are still a little bit left leaning. But we don't have these crazy densities anymore. You see, the density plots are quite well behaved. And the summaries are much more refined now. The high consumer actually consumes not 24, but something like 60 with a span of about the same length. But now we understand that the median actually lands much higher than we believed, because the data, recently people have started to consume more bitter chocolate than they used to. Second application, this is last slide. Second application is in the species distribution model. And we shift the gears quite a lot into geese. European gray goose, it's pictured over there, will start its own international species management plan. There is a formal way of regulating population, which that piece of legislation that is adopted on the EU level regulates how much can be harvested, how much conservation efforts should go into each species. And this species is last in a series of other European species that will go in under management from 2023. But the data is still sparse, somewhat contradicting, somewhat inconsistent between the countries. So there is quite a lot of uncertainty with regards to how much do we have, and they're the most abundant species right now, right? What we do have is GBIF, that's Global Biodiversity Information Facility, and these are observations from people that accidentally spot geese and they record it in the app, or people that go systematically and survey across the cross sections. For example, Lund University does that. And it's a mixture of both. So here are the spots where geese have been spotted between 20 and 22. The problem with this type of data, it's called presence-only data, is that it varies in terms of effort in sampling. Let's say places around the cities are heavily sampled, while places are out in the wilderness are basically not sampled because people don't go there on their free time. And detection is imperfect because if you're not looking for geese, you're not going to spot them, and zero counts are never recorded. So what we're trying to do in this paper is we're trying to complement with experts. We separate, first of all, separate the spatial process from the detection process. And then within the detection model, we complement it with expert judgment. So how likely it is that we will actually spot the geese if we go out without the purpose versus the cross-sectional surveying. So that's the last paper that we're working on, number 4. I'll take questions now from Andrew and then from the audience. These are the links again. We have slides and the report, which describes a little bit in more details, but I only have 20 minutes to talk to you today. And here's a package that you can install and play with these quantile-parameterized distributions, which are, I believe, quite nice.
Thank you so much, Dmytro.